Welcome to homework.
Okay, kind of our first task here is figuring out what 3R4R3 chloro 22455 pentamethylhexane looks like. So I'm going to draw pentamethylhexane. Okay, and we know that we've got a chlorine on carbon 3, and we know that we've got two methyls on carbon 2, we've got a methyl on carbon 4, and we've got two methyls on carbon 5. Now, we've also been told that the substituents of carbon 3 and 4 are R orientation. So let's just assume that they're wedges for now. That's what I like to do. And then figure out if that's R or not. And if it's not, then I'll change the wedges to hashes. Okay, this is the highest priority. This is the second. This is the third. Hydrogen's in the back. That looks like R, so a wedge is good. Okay, what about it over here? Okay, highest priority is this one, second highest priority is this one, methyl is the third highest priority, and hydrogen is in the back. That's counterclockwise, so that's S. So I know it's not a wedge to the methyl, it's a dash to the methyl, because the wedge gives us S, and we know it's supposed to be R. Okay, so now we have the correct structure of our molecule. And we are told that this is an E2 reaction. Okay, and we know something about E2 reactions, right? We know that the leaving group, in this case chlorine, has to be anti-periplanar to the hydrogen, right? That means we need to rotate the molecule about this bond such that we get something like this. Chlorine is on a wedge over here, and hydrogen is on a dash over there. That is anti-periplanar. Or we could rotate it so that chlorine's like this and hydrogen's like this. Or we could rotate it so that chlorine is on a wedge over here and hydrogen is on a dash over here. Either way, we need to rotate the molecule so that they are anti-periplanar. Currently, they are syn, right? They're on the same side of each other. And we can do this if you're comfortable, if you prefer, you can do like a Newman projection looking down that bond. If we did something like that, we would see something like this, that our chlorine and our hydrogen are like next to each other, right? And that's no good. This is what we'd end up with. So we'd have to do a rotation. If you're not comfortable with this and you prefer doing it the other way, that's okay too. The other way is just we move the hydrogen to where the methyl is, we move the methyl to where this group is, and we move this group to where the hydrogen is. We just swap them in that manner. So you may find that, hey, this is a T-butyl group. I don't know if you knew that or not, but a carbon with three methyls coming off is a T-butyl. So it may be simpler to go T, B, U. And now when we think about these swaps that I just talked about, moving the hydrogen to the methyl, I'll write Me in here for methyl, and the T-butyl to the methyl to the T-butyl and T-butyl to the hydrogen, then we can think about something like this. Leave the chlorine the same here. Okay, and we're going to draw a wedge to, okay, it used to be a wedge to hydrogen, but now we're going to have T-butyl up here. Okay, and it used to be a dash to methyl, but now it's going to be a dash to hydrogen because hydrogen moved to methyl, and it used to be a T-butyl down here, but now it's going to be a methyl. Okay, and now we find that, yes, we have exactly the situation we were looking for. Sorry, it's supposed to be chlorine here. Chlorine and hydrogen are anti-periplanar, right? And so if we wanted to do this with the Newman projection, that would be like rotating the rear carbon left, right? Hydrogen goes to where the methyl is, methyl goes to where the T-butyl was, and T-butyl goes to where the hydrogen is, such that the product would be, okay, we leave the front the same, but the carbon in the back, now this becomes our T-butyl, or I called it R prime, but now it's T-butyl. This becomes our hydrogen, and the methyl is down. And we see chlorine and hydrogen are anti-periplanar. That's exactly what we need. Same thing here. They're anti-periplanar. That's exactly what we need. Now, why do we need to do this? Well, because it turns out that if two groups are anti about the bond where the double bond is going to form, remember the mechanism here is that ethoxide ion is going to, well, I should draw it up here actually, ethoxide ion. It's going to come in, it's going to steal this hydrogen. The hydrogen carbon bond is going to stay behind. It's a double bond, and chlorine's going to leave. And we're going to get a double bond between these two carbons. And we need to figure out, okay, we've got a T-butyl and a methyl on one side, a hydrogen and a T-butyl on the other. You know, is it T-butyl, like, are the T-butyls on the same side or are they on opposite sides? You know, is it something like, you know, which of these two are we getting, basically? Okay, that's the question. Okay, that's why we need to know this. And basically, what it turns out is that if two groups are anti to each other, such as this T-butyl and this methyl, in the molecule, when we've drawn it such that the chlorine and the hydrogen are anti to each other, then these groups will be trans across the double bond. So we can just be like, okay, draw the double bond. The methyl's over here, T-butyl's over here, right? Which means that the T-butyl that remains has to be over here. It's the only place, which also makes sense because, hey, there's a hydrogen down here. These are anti, and there's a hydrogen here. Those are going to be trans, okay? So anti, when the molecule is oriented properly in terms of the leaving group and the neighboring hydrogen, means trans when we form the double bond. Okay, so now we know we need the T-butyl groups to be cis to each other in our final product. And that looks like the second option. They've drawn it like this. Right? And we'll notice, just as in the version we drew, T-butyls are cis across the double bond, hydrogen and methyl are cis across the double bond. Okay. That's option number 2.